How's it going, class? So this is going to be our sixth lecture, the first lecture of our second exam series. I hope you guys did good on the first exam. If you unfortunately did not, remember we have those extra credit opportunities that are located at the top of the modules. You're willing to take part, or if you're willing to take part, you can take part in any one of those. You can take a peek and see how long they take, which ones you feel like you'd be the most interested in. My research study is on there. I can't plug it. There's some UCF stuff where I can't really talk about it too much. It's just on there for you to look at. If you shoot me an email, I can give you more information about it, and I would love to do so. However, any one of those research studies will do, as well as you go on the UCF CHIPS page. You can look at research studies there. They'll all be really interesting, and we would love to have you come into the lab and give us some good quality data. If you want to do the IEPRS conference, that is coming up here, or that would probably already have passed by the time you guys see this lecture, or as well as you could do any other conferences coming up. We would love to see you guys come into the lab, though. That's usually what we try to push. So feel free to sign up for as many labs or as many research studies as you'd like. Unfortunately, for this course, only one of them will give you extra credit. But obviously, if you want to become more involved in the field, you want to become more involved in research, learn a little bit more about what we do here at UCF, you can become involved in multiple ones. But we'll get going into the lecture here. So this week we're going to be talking about training to improve strength and muscle mass. Hold on a second. I forgot to share my screen. There we go. All right. All right. Train to improve strength and muscle mass, right? So we're looking at some key definitions. So muscular strength, and this is often misconstrued just because people don't understand what true muscular strength is. So this is just the ability of the muscle or muscle group to voluntarily produce maximal force against an external resistance. So the maximal amount of muscular force or maximal amount of force that a muscle can produce. And so I see a lot of times people talk about, oh, you're doing like a 6 rep max. It's really not a measurement of muscular strength. Okay, it's used as a proxy measurement of muscular strength, but true maximal muscular strength is just the maximal ability of the muscle to contract to produce force. And then look at the next one here, hypertrophy is increasing the cross-sectional area of the muscle. So we'll get later, or a little bit later on, we'll talk about a few different types of muscular hypertrophy. But in essence, it's just the growth in size, right? It's just the enlarging of the muscle cells and the muscle bodies themselves. Okay, 1 rep maximum 1 RM. I'm sure we've all heard this before. It's just a maximum weight that can be lifted with a single effort. So this is in tandem with muscular strength. This is the actual amount of weight that can be lifted. Muscular strength is measured as a force, so like newtons or kilograms, or in some cases pounds. And 1 repetition maximum is just the amount of weight on the bar, the amount of weight in the movement that can be moved 1 time maximally. Force, so force is a push or pull that causes an object to start, stop, speed up, slow down, or change in direction. We all should know FMA, force equals mass times acceleration. So if you have heavier things, you need to apply more force to get them to move. Or if you have lighter things and you apply the same force, they will accelerate more quickly. Absolute strength is weight lifted or force applied. So what they mean by absolute strength is that's in comparison to relative strength, which is lifted or force applied divided by your body weight. So if you hear someone say like 80% of your 1 RM, okay, or you say 80% of your body weight, 70% of your body weight, that is a relative strength. If I said go squat 80% of your 1 RM 6 times, that is a relative prescription. If I were to say go squat 225 pounds, that is an absolute prescription. Much like if I were to say go run 70% of your VO2 max, that's a relative prescription. But if I said go run 8 miles an hour, that would be an absolute prescription, which means absolute is just a set value and relative is obviously relative to the individual. And then total volume load. So this is load times sets times repetition. So this is essentially looking at the amount of work that you were doing in an exercise routine. So we're going to begin talking about the muscle tendon complex. The muscle controls movements by transmitting force through passive components to the skeletal segments. So muscles move your joints. We should know this. Muscles move us. It was the name of our first lecture. When muscles contract, they can only shorten. So if we remember cross-bridge cycling, or that myosin pulls on the actin and pulls it like this, right? That is a shortening process. The way that muscles lengthen through an eccentric contraction is kind of an opposite manner, except your myosin heads are not actually crawling. What is occurring is instead of pulling on the actin actually kind of pulls on the myosin and stretches it, and then the myosin head pops off. And if you know that or if you've heard this before, you should know that eccentric contractions can produce more force than concentric contractions. That makes sense. During a concentric contraction, if you're looking at my arm here, and this is kind of a bad analogy, but it's best I can do, is as you go through a concentric contraction, you have the myosin head going through a power stroke, right? Your myosin head going through a power stroke, and usually it would detach, retach, and pull. If you're doing an eccentric contraction, the myosin head isn't bending the opposite direction. What's occurring is because the muscle is lengthening, the actin begins to pull, the actin begins to go this way, pull on the myosin head, and then it actually pops off of the actin. And so there's not actually any conformational change in the shape of the myosin, but it's sitting there trying to pull, and eventually the actin just pops off of it. So that takes a lot of force to do that. And that, in essence, is why eccentric contractions can produce more force than concentric contractions. And as always, all muscles are connected to the bone via a tendon, and that tendon allows to pull or to store passive energy. And what that means is that the muscle stays rigid, the tendon can store that passive energy, as well as if you hold a certain joint in a certain angle, that tendon can continue to hold that energy because the tendon is a relatively structured piece of your anatomy, and it's very hard to change the conformation of that tendon. If you've ever eaten red meat and you've got a tendon in there, you find that it's very hard to chew on. If you've ever pulled on it, it's very, very hard to pull on. That's its function. Okay, form follows function, like we've said before. And the function of the tendon is to store and to transfer the energy created in the muscle to the bones of the joints. So specificity of strength testing, right? Things we're going to look at is movement patterns. So complexity of the movement. When you are doing different types of strength testing and doing different types of strength prescription, you want to look at the complexity of the movement, looking at the posture and the joint positions, following each of those through their range of motion, and looking at the muscular actions. So we talked about this a bit before a few lectures ago, talking about like a squat. Okay, so when you're doing the squat, you want to look at the different movement patterns of that individual as well as the muscle actions. So as you go down in the squat, what are the muscles doing? How are the joints hinging? And as you go up in the movement, what are the muscles doing? How are the joints moving? And obviously, as you probably know, the squat is a relatively complex movement. You have a lot of moving parts. You're moving at the ankle, the knee, the hip. Usually you have your shoulders up, right? You're bearing down through your abdomen and through your thorax. It's a relatively complex movement. So there's a lot of things that can potentially be trained to enhance the force output or the strength output for that movement. Looking at the force magnitude, so basically just demands of the sport. So if you're looking at, let's say, a football player versus a wrestler, obviously as a wrestler you have to be explosive, but you also have to be able to hold people in grips, hold people in different movements. Versus in football, usually you're trying not to hold. You're trying to hit somebody as hard as you can. I suppose when you're wrapping someone up, you're tackling. But let's say basketball, right? You're trying to be explosive, cut and move. Very, very rarely are you actually holding on to somebody. So the force and the strength demands of that sport are going to dictate how you train your athlete. And then rate of force development. So this is really, really important. This has to do with power. When you're looking at somebody who has to develop force very, very quickly, you want to be training them in a manner in which they are developing force really, really quickly. This is that specificity principle. Specificity principle, excuse me. When you are trying to train an explosive athlete, you want to make sure that the strength training you are putting them through is an explosive movement. That's why you see a lot of cleans, snatches, and jerks in a lot of, or not cleans, but snatches and jerks in explosive athletes, because you want to be training those muscles and that movement in an explosive manner rather than training it in a more slow and controlled manner. So looking at muscular endurance as well, I think, pop up here. Sorry. There we go, muscular endurance. So muscular endurance is the capacity to perform repeated contractions or sustain a muscle contraction. So it's either something like holding a plank or doing repeated muscle contractions, like repeated push-ups, repeated sit-ups, right? Those are all muscular endurance type ordeals. Looking at the Army Fitness Test 1980 versus the Army Combat Fitness Test 2019, where we see there's a big difference in relative fitness. Obviously, the first test, or not the first test, but the test of the 1980 is a lot simpler. Just a push-ups, sit-ups, and a 2-mile run. Now they've begun to do a little bit more in-depth fitness testing to get a better overall idea of the overall level of fitness of their individual combatants or their cadets. And so this just shows that the military also is evolving. They're looking at different ways to measure fitness so that in order to provide the most adequate or the most well-equipped soldier to put on the field. This is essentially a breakdown hierarchy of the level of training, right? So at the very, very bottom, you have disease treatment. That's the minimal level of training. You just want to be doing some sort of training to make sure you're preventing or helping to mitigate the onset of a disease. Looking at rehabilitation, disease prevention, all the way up to the top. You guys can read through that. Essentially, that's just looking at the hierarchy of the intensity or the amount of effort that needs to put into each of these training styles. So we look at adaptations. We should know these. We have individuality, specificity, reversibility, progressive overload, and variation that we talked about in our last chapter, as well as we look at these adaptations. And we're going to get to talk a little bit more about what's happening specifically in these adaptations. So first thing we're going to talk about is the neuromuscular adaptations. So really what this means is that you have some sort of adaptation of the neural drive and the neural stimulation of the muscle is really what you're seeing in the first 8 to 10 weeks when you see those, quote, newbie gains, which I know I talked about before. A lot of people jump into the gym and they see these massive increases in strength and ability to move weight. It is mostly due to the neuromuscular junction and neuromuscular adaptations rather than the change in muscle itself. And for most adults, hypertrophy or growth in muscle size is how you gain muscle strength after that. But in children, you'll have those two factors as well as you'll have hyperplasia, which is an increase in muscle cells. Most adults don't actually increase the amount of muscle cells that they have. They're just increasing the relative size of those muscle cells. So we're talking about strength versus hypertrophy. So strength is the ability to generate force against an external load. Hypertrophy is just increase in muscle size. And so we look on the left here. Well, this guy is relatively large. He's a relatively large human being. He's not as big as this guy on the right. And that's because this guy on the left is a power trainer or a strength trainer. He's training specifically for strength. So yes, he is getting larger, but his training style is not meant to specifically elicit muscle growth and size. Now, this guy on the right is probably also on steroids in his defense. But if you were to compete these two or put these two against each other in just a strength competition, I can almost guarantee that the guy on the left will be stronger in terms of absolute weight, even though the guy on the right looks bigger. So training muscular endurance does not lead to significant changes in strength or hypertrophy. And we should know this. If you are an endurance trained athlete, if you are somebody who does a lot of running and a lot of calisthenics, those individuals are usually not as large as people who do heavy resistance training or do hypertrophy training. So strength gains cannot occur without neural adaptations via plasticity, but strength gain can occur without hypertrophy. And what we mean is, we're talking about is that with those strength gains, some of it has to do a lot with the neural adaptations, which I think we'll get into in a second here. Yeah, we'll get into in a second here, right? So the strength gains that are occurring always occur with neural adaptations. There is always some sort of neural change occurring when you are increasing in strength. But especially in novice individuals, you can get strength adaptation without muscle growth or muscle hypertrophy. And we'll talk about that a little more in detail in a second here. So with that, we know that muscle strength can result from resistance training as well as from increased muscle thickness, as well as muscle training can involve or can increase muscle thickness. So strength gains result from increases in muscle size and altered neural control. Hypertrophy is a major factor, but muscle size is not a direct parallel with strength. So that's like what we're saying before. Just because you are larger does not necessarily mean that you are stronger. So I've gotten this all the time. I get this quite a bit. I realize, or people will tell me that I look like I'm a relatively fit individual. People tell me that I look very, very strong. And while I might be somewhat of a fit individual, I'm actually not very strong. I spend a lot of my time doing hypertrophy training. So I always tell people that I'm actually probably a lot weaker than I look. When I compare myself to individuals of the same size, I often find usually people who are the same size or even smaller are stronger because they're probably doing more strength training. They're probably more disciplined. They work a lot harder than I do. A lot of the training that I do is specifically within the hypertrophy realm because I feel like that makes me feel the most fit and therefore it's the best for my health. But just because you are a larger individual does not necessarily mean that you are also a stronger individual. So looking at Looking at the first 8 to 10 weeks, strength increases are primarily due to neural activation. We talked about this before, that diminishing return, where you see this increase right here. And then as you begin to plateau, your neural adaptations have kind of plateaued off. And now you're relying specifically on muscle hypertrophy. So after the first 10 weeks, strength adaptation is more associated with muscle hypertrophy than with neural adaptation. Right, so for neuromuscular, what happens? What is happening in the neuromuscular junction? What is happening with the neuromuscular function that is causing these changes? And so we have changes in motor unit recruitment. And so we should remember Henneman's size principle. What's the order that we recruit muscle fibers in? Well, we recruit muscle fibers in what order? Smallest to largest, always smallest to largest. And so the structure and the capacity to which we can recruit motor units changes, and as well as the motor unit firing rate, the motor unit synchronization, as well as we have decreased motor unit inhibition. If that makes sense, if we are recruiting more muscle fibers for our movement, if we are increasing the firing rate of those muscle fibers, and if we are increasing the synchronicity or how much they work together during a movement, we're going to see increases in muscular strength. They're going to be able to move a load more. It's kind of like if you think of a bunch of people trying to push a really heavy load. Let's say it's people are trying to push cars, right? Your car's stuck. This is a good analogy for anyone that's from a winter state like myself. If you're all trying to push a car out of the snow, if you're all pushing at different times, you're not going to move that car. You do the 3, 2, 1 push, right? And you get everyone to push at one time, and you can move the car. Same thing within the muscles. If your muscles are not all firing its energy, if they're all firing by themselves, providing force at different times, it's really, really hard to produce a lot of force. But if they all fire at the same time, you're going to get a lot more force production, as well as you get decreased motor unit inhibition. So the signals that tell the brain and tell the central nervous system, hey, you're overactivating the muscles, slowly become decreased over time, because you're getting more used to that stimulus. Sorry, I'm having troubles with my mouse here today. I don't know why. There we go. Here we are. So rate coding. So this is what's occurring, what's changing for the most part that allows for more muscle activation. So rate coding refers to motor unit firing rate. How often and how fast is that motor unit firing? So successive activation of motor units can cause summation, increasing the firing rate, firing frequency that individual motor units fire increase. They increase the force generated. So you see here, you fire an action potential. I got my pen here. You fire an action potential, you can get force produced. Okay, you get force produced. You fire an action potential and then fire another one on top of it, you can get even more force produced. And then you get summation, more and more and more. And eventually you can get to a maximal level of tetanus where you are firing, you see here, you are firing over and 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 over, and you get a lot of muscular force production because you are keeping that muscle at its maximal tension. You're keeping it at total fusion or fused tetanus. So you get 100% of your maximal strength output. Active motor units can discharge at higher frequencies to generate greater tensions. And so essentially, like we said, you can fire more frequently. You can get these action potentials to occur more frequently here. We see how they're closer together than over here, which can allow for greater muscular strength. So looking at rate coding versus firing rates, there's two different ways that your muscles increase muscular strength. And what this is saying here is that smaller muscles rely more on rate coding. So they rely more on the individual signal sending, while larger muscles rely more on total recruitment. And this would make sense. Remember that our muscles fire pretty much in an all or none capacity. So if you think about this, my analogy that I like to use for this is if you're trying to fill up a beaker of water, but fill it up very, very precisely, okay? What would you prefer? What would be more precise if you had about 10 people using small little droplets to fill the beaker full of water, or if you had 2 people just taking 2 other smaller beakers and just pouring them all in at once, right? So obviously, if you're taking those 2 little bit smaller beakers and pouring them into the larger beaker, that's going to fill up faster, okay? But once you get to the point where you want to become precise, those 2 smaller beakers aren't as precise. And that's okay in large muscles. You don't need precision. But when you're looking at small muscles, like the muscles in the hands and the muscles in the eyes, you want very, very precise movements. And so that's why you rely more on motor unit recruitment, because if you're filling up that beaker with those small pipettes, if you're firing little muscle fibers one at a time to modulate that movement more precisely, you're going to get more of a controlled and precise movement than if you were firing the large motor units. This is pretty much more of what we're saying, right? After neural adaptation, the same absolute force can be generated at lower levels of motor activation. And so if you have neural improvement, essentially now you don't need to activate as many muscle fibers to get the same strength output. So now instead of having 15 fibers firing in random at different times to produce a set amount of force, you can get 10 fibers firing all at the same time to produce the same amount of force that 15 randomly firing fibers could do. We're going to look at the Golgi tendon organs. This is an inhibitory mechanism. So the Golgi tendon organs are sensory receptors that sense tension in the muscle tendon complex. So essentially, when you have force being produced in the muscle, you have Golgi tendon organs within the tendon, essentially telling the brain, telling the central nervous system how much tension is being developed. And because the tendon is a rigorous structure, if the tendon begins to stretch a lot, we know, okay, we're producing a lot of force. And so this happens when you have rapid changes in muscle length or muscle tension, and this is an antagonist symbol or signal. When the Golgi tendon organ is activated, it actually sends an inhibitory signal to the brain, to the central nervous, saying, hey, slow down, we're working too hard. If you didn't have the Golgi tendon organ, you would tear a lot more muscle fibers. And this is what happens when you have those cases of like extreme adrenaline events where you hear about like women lifting their cars off of babies, or people like being trapped under rocks. They will do this extreme event or this extreme extreme moment of muscular strength where they lift something really, really heavy that they would never, ever usually be able to lift. And then you find out afterwards that they had massive muscular damage. They have massive amounts of muscular tearing and tendon tearing. That is because of that adrenaline boost, that jolt of epinephrine, they are diminishing the amount the Golgi tendon organ is telling the body to have an inhibitory return. And so really what is happening here is that adrenaline is diminishing the signal from the Golgi tendon organ. So now there's no signal telling you not to lift more weight. And so the muscles are activating beyond their capacity and they're really just tearing themselves apart. So resistance training also decreases the sensitivity. So essentially what you're doing is over time in your resistance training is you are teaching the Golgi tendon organ, you are saying, hey, it is okay that we go to this level of tension. It is okay that we lift this much force. The muscle can handle it. And slowly over time, the Golgi tendon organ becomes more in tune with the muscle and can allow for more muscle force production. So looking at initial strength gains from resistance training, right? We can see strength gains as much as 25 to 100% in the first 6 months. And so this is really the misnomer of a lot of fit programs, of a lot of personal trainers. I don't mean to bash on personal trainers. There's some good out there and there's some bad, right? But what usually happens is a lot of these get fit quick, these get, whatever quick, get strong quick, is they take novice individuals and put them through a 3, 4, 5, 6 month training protocol. And they say, look at what I can do. I got my trainee up 100% in their squat. You should do what I'm saying. When in reality, you could pretty much do whatever you wanted in their training protocol and they would jump that high because of these neuromuscular gains. That's why if you were to actually look into the literature behind a lot of these get fit or get strong quick programs, you'll see that these are individuals that have never done resistance training. So of course, if they've never done resistance training, from what you've been taught in these lectures so far, you should know that they're going to see massive increases in their muscular strength. And then those trainers can turn around and tell the public, technically without lying, hey, if you do my strength training protocol, you'll get a 60% increase in your squat in 3 months. When in reality, if somebody who is relatively highly trained were to go in, they obviously would not see the gains like that. But again, in that capacity, the athletic trainer or the strength trainer isn't technically lying to the public. And so for relative strength gains, the relative amount, gaining 15, 20% is about the same between males and females and younger and older. But absolute strength gains, right, gains in absolute mass, right, tends to be the greatest in younger adult males. And this is just because the younger adult males are usually strongest by capacity. Usually the same size individual that's a young male will be stronger than the same size individual that's a young female or an older male or young older female, because we have a greater capacity compared to women and children in older populations. Essentially, we just have a lot more intrinsic factors available for us. I hate to say it, ladies, but biology is played against you here. men are just better able to put on muscular strength and hypertrophy because of a multitude of factors within our body. So we'll talk a little bit more about muscle hypertrophy here. So there's two different types. So we have transient hypertrophy, a pump. I'm sure you guys have all heard of a muscle pump. And if you don't know what a muscle pump is, we should kind of get a good idea of it from our last few lectures. A muscle pump is just the dilution or the increase in blood supply to the working muscle. And so what is literally occurring, let's say you're doing a bicep workout, and then you look down, you got the big juicy pump, you see the veins popping. Really what is occurring is because you are working out the bicep, because those muscles are working, they are calling for more oxygen and more metabolic removal. And so the blood flow to that area increases. And because the blood flow is increasing to that area, the capillary beds are becoming swollen with blood. And so the muscle itself is literally becoming swollen with blood. It's becoming saturated with blood, which makes it appear larger. And because the muscle is saturated with blood, the blood flow to it is larger. That means the veins returning from that muscle are also going to be larger. And that's why people that are working out get a big juicy pump. You see their veins enlarging because not only are their veins being pressed against the skin, but the veins are also getting larger themselves to allow for more blood flow. And then we have chronic hypertrophy. So this is increased muscle size in terms of actual increase in the muscle size because of some sort of intrinsic component. Let's say it be myofibrillar or sarcoplasmic, which we'll talk about in a second here. But essentially, this is actually increase in muscle size that will last over time. So we have three types of chronic hypertrophy. We have muscle fiber, sarcoplasmic hypertrophy, and then myofibrillar hypertrophy. So muscle fiber, initial state of the muscle, is growth overall, right? So we look at sarcoplasmic hypertrophy, and that is increase in the sarcoplasm. So when we look at this, what's occurring here is our myofibrils, right? Our actual contractile units are not increasing in size or increasing in capacity. What's occurring here is we are getting more storage capacity. This is what occurs when you do a little bit more endurance style hypertrophy training, is you're getting more capacity to store glycogen in these areas. And if you have more of a capacity to store fuel, you can work a little bit longer. Versus myofibrillar hypertrophy is actually muscular hypertrophy in terms of the contractile units. So this is more like strength training. This is what happens a little bit more in strength-based hypertrophy training, is you get more contractile units, you get more myosin and actin, and this will allow you to provide more force with any sort of movement. So that makes sense. In this case, essentially you have individuals, let's say you have 4 people, if you supply them a lot of food and a lot of energy, they're gonna be able to work for a long period of time. In this case, you don't have as much food or as much energy, but you have a lot more people, so you can get more force or more work done in a short period of time. So looking at that, more actin, myosin filaments, and then on the right here, more connective tissue. These are actually flipped. I apologize for this. This should be, the one on the right there should be the muscle fibers. This is the connective tissue, what we're talking about here. So this one right here, this muscle fiber changed. It doesn't really look like it's changing because we're actually talking about more connective tissue that we're talking about here, more connective tissue, elastic proteins, or collagen. So more of the extracellular increases versus this one also relates to the middle one up here, sarcoplasmic reticulum, and more actin and myosin filaments relates to this one right here. Sorry for that confusion that those are swapped there. So this is just a basic rundown of the proper training loads and intensities that you want to do for different individuals for different training styles. Something that I find specifically for muscle hypertrophy is that a lot of people know that they should be training in these areas. A lot of people that I talk to, specifically males, talk about how they train in the 8 to 12 rep range. But if you're trying to get stronger, that's not where you should be training. You should be training lower amounts of reps, as well as you should be doing higher intensities. And something else that's usually missed is the rest times. Something that is extremely important for your training durations is the rest times in between sets. When you're doing muscular strength, I know people always make jokes about power trainers. So they go and they lift a weight really heavy one time slowly, and then they put it down and they sit in a chair for 5 minutes and they fold out the lawn chair and they sit down in it and they chill. There's lots of memes about power trainers like that. What they're really doing is correct. If you want to train muscular strength, you need to allow for 3 to 5 minutes of recovery time in between each lift so that you can provide that maximal force output once more. Versus in muscle hypertrophy training, really what you're doing is you are trying to increase the total amount of muscle fibers that are fatigued. So you want to do an 8 to 12 rep range, and then you want to have about a minute to a minute and a half of rest time to allow for recovery of some muscle fibers, but not all of them, so that that window of fatigue will increase. And I think talking about this now is I'll probably do another lecture, a little bonus lecture on what the difference between all these are and their training styles. So if you're a little confused right now, we'll get into it in the next lecture. So still on hypertrophy. So traditional hypertrophy training volume, you have higher volume, lower intensity, and shorter rest. Short rest does not mean like 30 seconds. It means like a minute to a minute and a half. The modern approach is maximum warrior recruitment. So the overall goal is to achieve fatigue and to increase muscle damage. If you are increasing the amount of muscle damage, that means you are increasing the amount of adaptation, and more than likely you are increasing the amount of muscle size. Overall, your goal is just to provide a stimulus for muscle protein synthesis. So hypertrophy, possible causes, right? We have mechanical stress, swelling, hormones, cell damage, accumulation of metabolites, free radicals. These are all things that are said to stimulate increased muscle protein synthesis. And there isn't really any one that can occur without the other. If you have mechanical stress, but you don't have any of the hormones, you don't have any of the blood supply to it, you're not going to see increases in muscle size. Really, what you want to do is you want to have a balance of all of these factors, and all these factors are playing in to what is stimulating muscle protein synthesis. The training of momentary muscle failure can stimulate hypertrophy regardless of the load. And so essentially what they're saying is if you are trained to failure, you can still see muscle hypertrophy gains. And so now it wouldn't really be recommended to do something like 100 reps. What it's saying is if you do something for maybe 20 reps, but you do it to failure, you can stimulate muscle protein synthesis. So traditional hypertrophy training and low load to failure results in similar hypertrophy. And so what this is really saying is you can kind of mix up your stimulus for muscle hypertrophy training as long as you are going to failure within a smaller realm of possibility. So low load resistance training, although hypertrophy may be similar, strength increases are similar or lower during lower load resistance training. This makes sense. So if you're doing a low load resistance training, even though you're going to failure, you're not really stimulating, or you're not really testing the contractile tensility of the muscles. You're not really testing the maximal ability of your muscle to produce force. So you're not going to see a lot of adaptations in that. And that would make sense. If you're trying to get stronger, if you're trying to increase your 1RM, it wouldn't make a lot of sense to lift 10% of your 1RM 150 times, because you're not actually testing the contractile capacity of the muscle. Realistically, you're testing more of the endurance capacity of the muscle. So lower load, higher motor unit recruitment, higher loads result in greater neural adaptation. So with that, greater voluntary muscle activation with higher loads leads to greater strength. And so what we're trying to say here essentially is that's a typo. Low loads leads to lower motor unit recruitment. I apologize. Low loads lead to lower motor unit recruitment. And so what we're saying here is greater voluntary muscle activation with high loads will lead to greater strength. And that makes sense. Remember, that's that specificity. If you are trying to increase muscular strength, you need to have higher neural drive and more activation of the muscles so that you can have a higher stimulus to elicit more adaptation, to elicit more growth in muscular strength. All right, so moving on here. So strength, we talked about neuromuscular adaptation, motor unit recruitment, and firing rate. So remember, those smaller units, the smaller muscles rely more on firing rate, and those larger muscles rely more on recruitment. There's a biogenic shift, so decreased mitochondrial density and increase in enzymes associated with anaerobic energy. So increased ATP-PCR and glycogen storage, increased sarcoplasmic reticulum and T-tubules. So essentially, when you are training a lot more strength-based or hypertrophy-based, you are moving away from those things that are endurance-based. Right? We need mitochondria, we need blood supply for endurance-based activities. For anaerobic-based activities, this should make sense. We want more of the quick energy systems, the phosphagen and the glycolytic system. So because of that, we begin to decrease mitochondrial density, we begin to increase the ATP-PCR stores and increase glycogen storage so that we have more capacity to produce ATP via the anaerobic mechanisms, as well as you have somewhat of a fiber type shift. So the fiber type shift is not as prevalent from type 1 to type 2 because there are more things that need to happen. And essentially, once angiogenesis or the increase in capillarization has occurred, you don't really shift back away from it. But there is a little bit of a shift from type 1 to type 2A, but you don't really see type 1 fibers go all the way up to type 2B or type 2X. like you would see type 2X kind of shift a lot more types towards type 1. So in essence, what I'm saying here is the shift from type 1 to type 2 is a little bit more uncommon, a little bit more rigorous than the shift from type 2 to type 1, as well as we'll talk about pennation angle here. And so with this, pennation angle will change with chronic resistance training. So move toward optimal angle to produce force. So your muscles are not always in the proper pennation angle for force production. They're just in the natural way that they grow. Whatever movements you are doing, whatever specific movements that you are doing are going to apply stress to the muscle fibers within the muscle and are eventually over time going to change the pennation angle here. So we see here the pennation angle in a bipennate muscle is a little bit more steep here versus where it is here. You want it to be, or excuse me, is less steep here than it is here. And so if it's less steep, like it is up here, this muscle is going to be better for faster contractions because the muscles are shortening more in parallel. But if you have a steeper conformation, while the muscles are shortening in this conformation, they're not actually shortening the total length of the muscle body. And so this makes that muscle better for muscular strength than it does for muscular velocity. Looking at this at descending versus ascending and bell-shaped force curves. And so these are different types of force curves having to do with portions of the movement. And so one that we'll talk about here, these all have to do with the relative length tension relationship. And so we remember is that these muscle fibers, or these myofibrils, they have an optimal length for contraction. Up here, these are too far apart, and right here, these are too close together. So there's that optimal level of muscular contraction that we see here, as well as we have to remember that those change throughout the range of motion. And so when you have, let's say, a bench press or a squat, we should know that the hardest points of the bench press or the squat is the bottom part, and that makes it a descending force curve. As you move down through the movements, or as you move to complete the movements, the amount of force that you can produce is decreased. And that's why the bottom of a squat or the bottom of the bench press feels the heaviest, because your muscles are actually the most mechanically disadvantaged there, which means it's the hardest for them to produce force. And therefore, that weight is going to feel heavier in that motion. Now, something that has a bell-shaped force curve is something like a curl. So if you were doing a curl, okay, if you're holding your arm down by your side and you're doing a curl up, when you are at the full extension, the movement is relatively hard. And when you are at full flexion, the movement is relatively hard. But right in the middle is the most mechanically advantaged position for your biceps to produce force. And therefore, that is a bell-shaped force curve. And that's kind of like what we're looking at here, 1 through 5, right? This is the relationship of all muscle fiber length tension relationships, but specifically for the biceps, since it's just a single joint movement, it follows this thing up here. It follows this right here perfectly. So if it's too long, you can't control, or you can't produce a lot of force. And if it's too short, you can't produce a lot of force. The reason that a squat and a bench press don't follow that perfectly, and they have the complete descending force curve, is because it's a complex movement. We have a lot of moving parts. And so therefore, the greatest summation of mechanical disadvantage is at the bottom of the movement. And then an ascending force curve would be something like a hamstring curl. A hamstring curl, you have the greatest amount of force production at extension. So when you're doing a hamstring curl, if you're laying down or you're doing RDLs, you actually can produce the most force at extension of the hamstring versus at flexion, where you begin to lose a lot of that force production. So talking about accommodating resistance for this. And so as you move through, let's say, a bench press, what they do is obviously, right, like I said, the hardest position of a bench press is at the bottom. So when he has the bar on his chest here, let's say the bar is on his chest here, most of these chains are on the ground. But as he lifts the bar, and that movement becomes easier, the chains begin to lift off the ground. And so essentially what you're doing is, for the stronger portion of the movement near the top, you are lifting more weight than if you were at the bottom portion of the movement. So you'll see this done with bands as well. And so like a deadlift. So deadlifts, the bottom portion of the movement is the most difficult portion of the movement. So in the bottom portion, these bands are not very stretched. But as you lift and as you go through that force production curve, it becomes easier because you are allowed to produce more force, which is also the same time that these bands are becoming more stretched. And so as you move up, you are able to produce more force. as well as the bands are providing more resistance against you. And so this is a good way to train the entire movement rather than training the bottom of the movement. So really, when you're doing squats, you're doing bench presses, you're doing deadlifts, all you're really doing is training the weakest point of the movements. You're not actually training the entire movements. You're training the sticking point. You're training the bottom part. You're training the point at which it is the most difficult, because that is the maximal load that you can produce. So we've all seen this before when people are in the gym and they're squatting a ton of weight, but they're barely moving their legs at all. That is because they are in the upper echelon of the force curve. They are in a position in which they are most mechanically advantaged, and so they can produce the most force. But if they were to drop down all the way to 90 degrees, they would not be able to lift that weight, because much like if you were actually going to 90 degrees, you were only training that smallest, weakest portion of the movement. And so doing different training styles where you don't actually go to 90% squat knee flexion is actually good for some sport, because you think about it, in sport, when do you actually go to 90 degrees knee flexion? When are you sitting on a basketball court or in a football court in actual 90 degrees knee flexion? Almost never, right? So there's this huge push in the industry to have different strength training modalities like you see on the right and on the left here, that train the actual useful portion of the movement, the more upwards portion of the movement, so it can be more easily translatable to sport. So frequency, so focus on frequency and achieving minimal effective load each session. So by incorporating another training session instead of increasing volume during sessions may allow for great adaptation. So what this is saying is that you increase the frequency of your training sessions. Let's say you do like 2 a days. This may allow for greater adaptation. The rationale is you create another anabolic window to drive adaptation. So more volume does not necessarily increase anabolic response over a given threshold. So what it's saying is let's say you do a given volume, like a work volume total. You do a given volume, let's say it's let's say the arbitrary unit is 100, okay? And let's say that is the maximal amount of stimulus your body can receive. Now, if you do a training session that's 150, your maximum training stimulus is still 100, right? So if you're doing 150 and the maximum training stimulus is still 100, you're doing a lot of extra work to get the same exact response. Versus, as let's say you do a training load at 75 and a training load at 75, now you're getting a total anabolic window or a total training load of 150 rather than just the one session of 100. So I know that doesn't make a lot of sense because they're arbitrary units, but I'm trying to explain how if you go to a certain point, any training past that point does not allow you to have an increased anabolic window. And that's why the idea of spreading it out so that you can have 2 maximal anabolic windows instead of having 1 anabolic window where you're overreaching might be better for muscle protein synthesis. So microdosing, focus on total volume and work over a week rather than specific sessions. So what this means is this is not microdosing in the way that most people think of with microdosing with stimulants or with mushrooms, right? This is microdosing with exercise. So this is you microdosing your exercise doses over the week rather than lumping it all into one. And this is something that I feel like a lot of individuals do that are not obviously trained, is that they go to the gym maybe twice a week and work out really, really hard for like 2 hours, and they don't see the strength gains that other people see when they're working out, let's say, like 6 times a week. So benefits of resistance training. There's lots of benefits of resistance training, and this is something that is becoming a lot more prevalent in outside of sport practitioners, is that they're finding that strength training is really important for rehab and activities of daily living. So you have better joint stabilization control, improved balance, so you have lower risks of falls. So obviously for us that are young, we don't really worry about falling too much, but for those who are in the geriatric population, falls are a big risk for them because that usually leads to a massive decrease in their standard of living. You increase bone mineral density, improve glucose metabolism, all these things that you see here. I'm not going to list them all out, but essentially what the gist of this is that there is a massive amount of improvements that can be seen in your everyday life just from strength training. So this is just essentially a flow chart looking at what happens to your relative strength over time. And so your back strength, arm strength, leg strength, once you get to the age of about 25, 30, if you do not continue resistance training, you begin to see this drop in your muscular strength. And so for adult life, what we want to do is if you can continue to train or do strength training, you can maintain that muscular strength. And that makes sense. Obviously, if you're doing strength training, you're going to maintain your muscular strength much more in a much more capable manner than if you were to not train at all. And you're going to see this drop off much, much earlier. So bone mineral density, right? The mineral content of the area mineral content in an area or volume of the bone. So essentially, this is just saying how structured or how mineral dense your bones are. The more mineral dense they are, the more structure they have, and the stronger that they are. And so, if you remember Wolff's law is explaining that you stress the bone, just like if you stress the muscle, the bone will react and become stronger. And so, this has to do a lot. If you look at, let's say, you look at baseball pitchers, this is a really good example. If you look at like the DEXA, if you look at my DEXA since I pitched since I was 12 years old until I was 24, you will see that the musculature in my right arm is obviously larger because I throw with my right arm, but also the bone structure, the humerus itself is actually 15% larger the last time I had DEXA done. It's 15% larger in my right arm than it is in my left arm because of all the force and the constant torsion I've placed on my arm from throwing a baseball. And if you look at any baseball player, you will see this pretty much for all individuals that have played since a young age and play into their adulthood. If you look at major league players, you can see a massive change in their bone mineral density from arm to arm. And they'll even get to the point where they start doing specialized training with their off arm so they can keep a balance between the two arms. But essentially, right, we're seeing what's happening here with osteoporosis is this bone mineral density decreases. And so, as you can imagine, lost my cursor here. As you can imagine, the bone mineral density on the right is lower here, and this is going to allow for a more fragile bone. So looking at resistance training here, so looking at bone mineral density here. So we see at the controls that bone mineral density is well below 2000, but as you go through resistance training, you have this 20% increase in the amount of bone mineral density or bone mineral components. So that's the gist of what we're going to talk about today. I'm going to keep going here, though. We're going to talk about some myth busters here. So these are things that are pretty prevalent, things I want to talk about in literature and in common society about strength training that are usually misnomers and usually misconstrued and not taught correctly. So we're going to talk specifically about a few things here. So don't end the lecture here, as I think that you'll enjoy a lot of these. And this is technically still part of the lecture. This will be testable material. So what's good, what's bad, and what's okay? So muscle protein synthesis, right? So this is the anabolic window. Amino acids are incorporated to make protein. Muscle protein breakdown is catabolism or the catabolic, and the breakdown of body proteins and amino acids. So catabolic during a workout, when you are working out, you are in catabolism. You are breaking down the muscle proteins. That makes sense. You are working out, so you are breaking down muscle proteins. So it becomes anabolic resistance. So you want to become anabolic. Don't know what. That's a typo there too. I apologize. So ignore that. So you want it to become anabolic after your workout. I want to say time, not age. So you want to become anabolic after your workout. And so maximizing skeletal muscle protein synthesis requires at least 20 grams of essential amino acids. So essentially what you were trying to do is you are trying to move yourself from this catabolic window, this catabolism that's happening during the workout, to an anabolic state where you can have muscle protein synthesis during or soon after your workout. And so what you're really seeing here is that resistance training induces a sustained increase in muscle protein synthesis up to 48 hours, which likely sensitizes the muscles to feeding. As a result, feeding during this time should result in greater muscle protein synthesis response compared to feeding with rest. And what we're saying here essentially is that muscle protein synthesis increases when you feed or you eat after a workout. And so you see this control level here when you're fasted after a workout, that's your level of muscle protein synthesis. But if you eat right after your workout, most people know the window of anabolic opportunity is that post resistance training window where you want to be having carbohydrates and specifically proteins so that you can increase or you can stimulate the highest amount of muscle protein synthesis. And so this is said in literature a lot, or said in common literature or common society a lot, is that you want to have your protein right after you work out. And that's true. You want to have carbohydrates and high protein meals or protein shakes right after you work out because it's going to stimulate higher levels of muscle protein synthesis. And you want to do it probably within the first 2-ish hours. The earlier you can do it right after your workout, the better. But within the first 2 hours is usually pretty good to go. So this is just general protein recommendations for each type of exerciser. So this is another thing that has become misconstrued in literature. I remember when I was lifting a lot in college and you would hear people say, oh, you want a gram of protein per pound of weight. If people are like, that's way too much, you're going to blow up your kidneys, you're going to die from urea poisoning, you're going to die from nitrogen poisoning. That's not true. If you are a resistance trained individual, you can have up to 1 gram per pound. I would say for most people, and a lot of literature would say for most people, that if you were going through any sort of resistance training, you want at least 0.7 grams per pound of body weight. So if you are, let's say, 200 pounds, you want at least 140 grams of protein every single day. And if you are resistance training hard, you want at least 1 gram of protein per pound of your body weight. So this is something that you hear a lot of dietitians, they will be like, no, 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 you don't need that much. You don't need that much. You'll be fine. You'll just get rid of it all. If you dose it properly, if you take small feedings, we'll talk about in a second here, you take small feedings like we're going to talk about here, you can get massive increases in muscle protein synthesis. And what this is essentially saying is that the intermediate dosing where you have 20-gram meals frequently throughout the day is the best way to stimulate muscle protein synthesis. So we see here on the right, these grayish bars, you're seeing a lot more muscle protein synthesis than if you were to have bolus feeding of 40 grams a piece or have small, even bite-sized feeding. And so 20 grams to 30 grams per feeding, about 4 to 6 times a day, seems to be the best way to initiate muscle protein synthesis and allow for the best amount of muscle growth over time. And so I know there's going to be some people that push back on this and they're going to say, no, that's too much. That's too much, too much. I encourage you to read the newest literature, to read the systematic reviews, meta-analysis that have been published recently in the last 5 years on this, as we have found that increasing your protein intake in your diet has actually no negative contributions to any sort of negative outcome in terms of health or disease. Really, what's happening is not only are you stimulating muscle protein synthesis, but protein is also extremely good for your digestive tract, much like fiber is. Protein is the most satiating nutrient, which means it's going to keep you full the longest and also make you feel the most full acutely, as well as when you don't use most protein, you just pass it. And so that's also the argument. People will be like, oh, if you eat too much protein at once, you'll pass it. Yes, that's true. If you eat 80 grams of protein in the meal, your body can't really process that much protein. But even though you're passing it, you're still kind of filling that tank per se. You're providing yourself with the most amount of muscle protein synthesis because you are feeding it the most protein possible at any one point. And the worst thing that's happening is passing it. So in terms of wasting money, yeah, I guess you're wasting money a little bit, but actually there really is not a negative outcome to eating too much protein rather than just passing it through your stool. As well as you want to make sure that these whey proteins are giving you specific essential amino acids. In this case, leucine is a really, really important one. So if you look at your whey proteins, you look at your plant-based proteins, you will probably see that leucine is the highest concentration or the most prevalent amino acid in that whey protein, because that is actually the most essential amino acid, because it is the least prevalent within your body and is the hardest amino acid to achieve from a normal diet. Really what this is saying is that muscle protein synthesis may have a lot more to do with consumption of protein throughout the day rather than just stimulating it right after your workout. And so obviously the best time is after your workout, but don't just consume protein right after your workout. You should be consuming protein throughout the day in the small 20 to 30 gram increments, and then maybe boost your intake right after your workout and then go back to the small increments there on forward. So essentially, our summary here is strength increase can occur independently of hypertrophy. Increased strength is a result of neuromuscular changes in hypertrophy. So what we're saying here is that strength can occur in a neuromuscular way rather than just in a muscle size growth way. So those newbie gains right away are mostly due to neuromuscular changes, as well as just because somebody is larger does not mean that they are stronger. Again, I'm not a very large person. Compared to some people, I might be a little bit larger of a person, but I get it a lot with people like, oh, you look like you must be super strong. And I always kind of laugh at it because I'm like, I think that I'm really, really weak. I think that I just look kind of strong. And then I just, because of the way that I work out, it's the point is though, is that because my training style is different, because I don't really train for muscular strength, I look much less, or I am much less strong than I look. And again, not that I look that strong, but people that are usually my same size are much, much stronger than me. So transient hypertrophy occurs in a single session. So this is that pump. This is due to that blood flow and that increased saturation of blood within the muscle. Hypertrophy is due to contractile proteins, myofibrils, sarcoplasm, or connective tissues. That is your chronic hypertrophy. So the chronic hypertrophy is the actual change in the muscle hypertrophy or the muscle structure over time. Resistance training causes muscle protein synthesis for exercise. So resistance training stimulates muscle protein synthesis. Resistance training is important for quality of life, increased bone mineral density, and overall health. And so this is actually what my thesis was on in my master's, was that yes, cardiorespiratory health is becoming a great track of long-term health and lower mortality, but increased muscular strength is also becoming a massive cost. So we found that just a 5% increase in your muscular strength equates to a 16% decrease in all-cause mortality, as well as a 14% decrease in cardiovascular disease prevalence. So just increasing your muscular strength a little bit decreases your chances of dying by 16%, which is a massive change and a massive production into the literature, which previously thought that only cardiorespiratory strength or cardiorespiratory fitness was good for long-term duration health, when in reality, they're probably both important. If not, muscular strength might become a little bit more important over the time, because muscular strength also involves getting you through activities of daily living, like just standing out of a chair. If you're stronger in your geriatric age, you are more able to perform activities of daily living. So your anabolic window lasts for hours to days. Obviously, like we said on that, or we saw on that one graph, the best time to hit your anabolic window is within a few hours after your workout. So again, small doses of protein throughout the day, maybe a little bit larger one right after your workout, and then back to the small doses. And then recovery and nutrition increases muscle protein synthesis. So again, you want to be balancing the workout with the recovery with proper nutrition, and you need to have all three of those things in tandem to get the best muscle protein synthesis, the best gains, and the best improvement in your sport. That's going to be the end of the lecture here today. I hope you guys enjoyed it. I hope this being a little bit more applied to what you're probably doing in the gym with your patients or with the people that you are personal training or whatever it may be. Hopefully that these concepts kind of carry over. And I think that this is really important because a lot of what I hear in the field is completely incorrect. And when I say these things, I almost don't like talking about what I do and what I'm getting my PhD in and what I do research on around gym culture, because a lot of people think that it's all hoopla, when in reality, I've read hundreds and hundreds of hours of literature written by people that are much, much smarter than I am and agreed on by people that are much, much smarter than I am. And so when I say these things, I hope that you guys take these things to heart and understand that this is the newest level of literature. This is the newest ideas for what we have for strength training and for muscle hypertrophy and everything like that. And that this evolves over time. So what you were taught in high school 5, 10 years ago, for me, that's 10 years ago. But if you're maybe it's 5 years ago for you, what you were taught then has probably changed a little bit. And what I'm saying right now will probably change a little bit a decade from now. But for now, this is our best evidence practice. All the studies that we have, the systematic reviews and meta-analysis, these ideas are what we think will work the best. And I hope to spread this out into the world a little bit more, help to spread this out into personal training, athletic training, physical therapy a little bit more, because some of the practitioners that are out there rely on 30-year-old evidence rather than looking at the new evidence. I implore you, as you go through your careers, to make sure you are always looking at new evidence. Yes, something else works, but you never know if it could be working better. And if you're trying to change the lives of somebody who may have a detriment, who may have a disease, who may be in rehab, you want to make sure that you are providing the best standard of care for them. But I hope you guys enjoyed the lecture today, and I will see you next time.